session, let us continue to discuss on Fourier series. So in the last two sessions, we have seen an introduction and obtain a Fourier series expansions in the interval minus pi and pi. So let us continue to do when a function is even. We have discussed in the as said in the earlier sessions, if a function is even, we're going to evaluate only a0 and an, and bn will be 0 automatically. And if the function is odd, only bn need to be evaluated. A0 and an will be equal to 0. That is what we have learned. So what if the function is neither even nor odd? Such cases will be discussed in detail in this session. So again we are let us recall what is a Fourier series, an expansion of a Fourier series, and the expressions for a0, an and bn. So f of x is equal to a0 by 2 plus an summation an cos n pi x by l plus summation bn sin n pi x by l, where a0 is given by 1 by pi minus pi to pi f of x dx, and an is 1 by pi integral minus pi to pi f of x cos n x into dx, and bn is minus 1 by pi integral minus pi to pi f of x sin n x into dx. So let us see few more examples. So obtain the Fourier series of the function f of x is equal to x minus x square in the interval minus pi to pi, and hence deduce that 1 by 1 square plus minus 1 by 2 square plus 1 by 3 square minus 1 by 4 square and so on, pi square by 12. And this question, especially it has been asked in the VTO examination in the year 2006. So it has been asked in the other years also. So only a few I could mention here. So now, as the procedure says, consider your f of x, which is x is equal to, f of x is equal to x minus x square. And now let us check for the function whether it is even or odd. F of minus x is equal to minus x minus of minus x whole square. So when we simplify this, we get it as minus x and minus x square, which can be written as minus of x plus x square. So this is what we have obtained. This is neither equal to f of x nor equal to minus f of x. So therefore, we cannot come to any conclusion that f of x is equal to x minus x square is an even function or an odd function. So we write down that as f of x is equal to x minus x square is neither even nor odd. So in such cases, where we are unable to justify or unable to judge whether it is even or odd function, then it is that we need to evaluate all the three Fourier coefficients a0, an and bn. So let us evaluate an now. A0 is equal to 1 by pi minus integral minus pi to pi f of x dx. So let us substitute for f of x, which is x minus x square, and integration of this, integration of x is x square by 2 and integration of minus x square is minus x cube by 3. And this integrand, whatever the answer we had got it, must be evaluated between the limits minus pi and pi. So when we substitute the upper limit and lower limit, this is for the upper limit and this is for the lower limit, and further simplifying it, we get it as minus 2 pi cube by 3, and the answer is going to be for a0 is equal to minus 2 pi square by 3. Now consider an. An is equal to 1 by pi integral minus pi to pi f of x cos nx dx. Substitute for f of x. F of x is x minus x square into cos nx dx. So x minus x square is the first function, cos nx is a second function. And we doesn't know whether it is an even function or an odd function. There is no such we doesn't know this entire product. Since we doesn't know x minus x square is even or odd, even if cos nx is even, product of these two functions, whether it is even or odd, we will not be able to do it. So the integrand and the limits also must be kept as it is. So since there are product, one algebraic function and one trigonometric function existing in the product, and we need to apply Bernoulli's rule for integration. Keep this 1 by pi as it is. First function, integration of cos nx is sin nx by n minus minus integration of, so first function must be kept on differentiating and second function must be kept on integrating it. So first function differentiation is 1 minus 2x and integration of this is minus cos nx by n square. Again differentiate this, so we get it as minus 2, and again integrate, we get it as minus sin nx by n cube in the interval minus pi to pi. So the next term would be 0 because differentiation of minus 2 will be 0. So now substitute the upper limit minus lower limit. So when we substitute the upper limit, we know that sin n pi is 0 for all values of n. So first term there will be 0. 0 multiplied anything will be 0. Cos n pi is minus 1 to the power of n. Again sin n pi, this term will be 0. So first term gives you 0, second term exists, third term will be 0 for upper limit. For lower limit again, sine of n is equal sine of x is replaced by minus pi. So sine of minus theta is minus sine theta. Again we get back sine n pi. So sine n pi is 0 again. So second term gives us this and third term becomes 0. So now let us further simplify. The common term here is minus 1 to the power of n by n square. Take it outside. 1 minus 2 pi minus of 1 plus 2 pi. When we simplify we get minus 4 pi. So further simplifying we get the answer for an as minus 4 into minus 1 to the power of n by n square. So this is how we need to evaluate an. And since we could not come to any conclusion like a0 and an need to be eliminated or only bn need to be evaluated, nothing like that. So all the three Fourier coefficients we are evaluating it. So consider bn now. The formula is 1 by pi minus pi to pi f of x sin nx. Substitute for f of x, x minus x square into sin nx and integrate by using Bernoulli's rule. So this is our first function and this is our second function. Keep differentiating the first function and keep integrating the second function. Alternate plus and minus term should be entered. So first function, keep it as x minus x square, integration of second, that is minus cos nx by n, and differentiation of first function. This differentiation of this is minus 1 minus 2x and integration of this is minus sin nx by n square. Differentiation of this is minus 2 and integration of this is cos nx by n cube between the limits minus pi and pi. Now substitute the upper limit and lower limit. When we substitute the upper limit, this is what the expansion we get. Sin n pi is 0 always for any value of n. Cos n pi is minus 1 to the power of n. So here this term we get it and again this term we will be getting it. And for the lower limit again it is the same. Cos of minus theta is cos theta itself. So the same answer we will be getting it. And further simplifying we get the answer as this and minus again can be added here. So minus 1 to the power of n plus 1 by n. So Fourier series f of x is given by a0 by 2 plus summation an cos nx plus summation bn sin nx. We have evaluated a0, an and bn values which you can substitute it here. So on substituting for f of x, x minus x square, a0, an and bn values, we get this expansion. Further simplifying we can get this. So only the simplification happens here. Again it becomes minus pi square by 3. And now we need another answer. So if it is only the Fourier series expansion, we can stop it at this stage itself. But the answer expected in the problem is something else. So let us, in order to evaluate that, we have to go further. In order to do that, so if you have to think very carefully whether you have to keep this term or this term. When you look at the answer, n is taking all the possible values 1, 2, 3, 4 and they are also having square. So it means that this term should be kept and this term need to be eliminated. This term can be eliminated. And in order to eliminate sign, the best value can be substituted as x is equal to 0. So put x is equal to 0, we get this expansion, this becomes 0, pi square by 3 can be transferred towards other side and this term is there as it is. Now expand the summation by giving the values for n. n is equal to 1, 2, 3, 4 and so on. When n is equal to 1, we get this term. When n is equal to 2, when n is equal to 3 and when n is equal to 4. This is the required answer for us. So hence we can conclude that the problem and the expansion and the required answer is obtained. Similarly, let us see another example. Obtain the Fourier series for a function f of x is equal to e to the power of minus x in the interval minus L and L. So here interval is slightly different. So we have to check the original formula. So original formula is actually to L and minus L, whereas the specific case for L, if L takes the value pi, then we get minus pi to pi. So this is actually the original formula or original interval where L can take any value. That is what the meaning here. So as usual, f of x, consider f of x and check for the even function or an odd function. So and we conclude that this is neither even nor odd. So we need to evaluate a0, an and bn. So to evaluate an, in the interval minus pi to pi, the formula is slightly different. In the interval minus L to L, so you have to consider this. A naught is 1 by L minus integral minus L to L f of x dx. F of x is e power minus x. Integration of that is e power minus x by minus 1. Substitute the limit. Upper limit minus the lower limit. This is what we get. And this is in the form of e to the power of minus theta minus e to the power of theta. Interchange. E to the power of theta minus e to the power of minus theta by 2 is sine hyperbolic. So minus is missing there. So what we can do is we can interchange the term. Minus and minus becomes plus there. 2 sine hyperbolic L by L. That is what is our A naught. And an is equal to, the formula is 1 by L integral minus L to L e power minus x cos n pi x by L. So imagine this is a standard formula actually for A naught and an, whereas if you put L is equal to pi everywhere, where and all you have L, if you replace it by pi, you get an formulas for integral minus pi to pi cos nx, all that is for the previous problems. So this is actually the original one. So if you put L is equal to pi, pi and pi gets cancelled, you get cos n pi. That is what we have used in the earlier problems. So an is this formula, the standard formula. And now integration must be done. So here you cannot apply integration by parts or Bernoulli's rule because none of the functions are vanishing after few number of derivatives. So that is the reason we need to use the formula. The formula is, let me write you the formula. Formula is integration of e to the power of ax into cos bx. Actually cos bx plus c, that is, so here we can take it as cos bx into dx. So the formula for this is e to the power of ax divided by a square plus b square into a cos bx minus plus b sin bx. So this is actually the formula. So the same formula is used with a is equal to minus 1 and b is equal to n pi by L. So substitute that, e power minus x divided by a square, that is minus 1 whole square, and b is n pi by L the whole square, and minus 1 into cos, okay, this is a cos bx, so a is minus 1, b is this, and n into sine n pi by L into x. So we have just made a substitution for a and b. Now further simplifying it, that is actually the integration, and between the limits we have to evaluate. So x is equal to L and x is equal to minus L. So substitute the limit, we get for the upper limit this, and this is for the lower limit. Where and all you had x, replace it by x, replace x by L here and replace x by minus L here. And simplifying further, cos n pi is minus 1 to the power of n, sin n pi is 0. So cos n pi is value is entered, sin n pi value is 0. Similarly, cos of minus n pi is again minus 1 to the power of n, and sin n pi is 0. So further simplifying it, we get this expansion and take a LCM on the denominator and cancel the terms whatever it is getting cancelled, and simplifying this term, multiply and divide by 2 and convert it as sine hyperbolic. So therefore we get this expansion for an. Now a naught and an is done, we have to evaluate bn. Bn, the formula is this. So again I am repeating, this is actually the original one. In this, if you take L is equal to pi, you get the formulas for minus pi to pi. So it's better to remember this set of formula itself instead of that. So this is integration. Again, none of the functions are vanishing, so you need to apply the formula. So formula for this is integral, just a minute. Yeah. So here, integral e to the power of ax into sine. So in the previous case we had seen for cos, and now it is for sine bx. So the formula for this is e to the power of ax by a square plus b square into a sine bx minus b cos bx. So this is what the formula is actually. So use the same formula and enter a is equal to minus 1 and b is equal to n pi by L. So we get this expansion between the limits minus L and L. Substitute the limits, upper limit minus the lower limit. So when we substitute upper limit and lower limit, then cos n pi, sin n pi values need to be substituted. So this is what the expansion we get. And now further simplifying it, In the numerator we get this term, denominator this term. You can take LCM. LCM is L square in the denominator, L in the numerator. So when we simplify further, we get this expansion. So this is a value for Bn. So nothing can be mucked up or nothing can be remembered here. So only thing is, only when you work out these problems more number of times, you get the confidence. So all the problems must be solved and checked for the answers. Don't just read. That is the sincere advice that I always give you for the students. So now substitute, you have evaluated A0, An and Bn. Substitute those values in the Fourier series expansion. This is the Fourier series expansion. And when we make a substitution for A0, An and Bn, we get this expansion. So common term is sine hyperbolic L. Take it outside. And this is what the answer we get. So this is how you need to evaluate the problems in the interval minus L to L. The formulas which we have used for minus L to L are actually the original formulas. And if you replace L is equal to pi, then you get the set of formulas for minus pi to pi. Okay, so you need to remember them in a proper way, in a correct order also. So this is about the expansion, Fourier series expansion, when the function is neither even nor odd and in the interval minus L to L. So if there is any doubts, get back to me.